Okay, we're back with the third of our videos here going over the review problems for Unit 4. As always, you should look at the problems as I give them to you, pause, work them out yourself, and then check your answer. We're going to be working these the most efficient way possible with the calculator shortcut programs and apps. Number 13. The heights in inches of several married couples were measured as recorded. The husband's height 72, 70, 68, 65, 67, and 69. That would be, I think it's in inches here. And the wife's height was 68, 66, 66, 67, 65, and 64. Construct a 95% confidence interval for the difference in heights of the married couples. Press pause now. First of all, notice that this is actually paired data. They're not the same person, but they are in a couple, so we're going to see how they compare within the same couple. So they are not independent. They are a dependent set. They're paired data. So we're going to treat this as one sample. So I typed the data for the men, the husbands, in L1, for the women, the wives, in L2. For L3, we're going to do the difference. And we do husband's height minus wife's height the way I did it here. So that's in L3. So you put your cursor up on the label for L3. Type in L1 minus L2. That is second 1 minus second 2. Enter. And all of the values will be computed for you correctly in L3 for the subtractions. Then we run an interval. T-interval, but we're doing it on L3, which is what they want, the data that they want. So data is in L3. A confidence level is 0.95. Have it calculated, and it calculates the interval there from negative 0.13 to 5.13. So we're 95% confident that the difference in height is anywhere from 0.13 the husband being 0.13 shorter up to being 5.13 inches taller than the spouse, or than the wife on this this setup here. Okay, X bar is right in the middle of that interval, which is 2.5. So on this particular sample, the husband averaged 2.5 inches taller than the wife, and the standard deviation was also about 2.5, 2.50998, and the N was 6. For this to work, we would really need those L3 values to be not too highly off of normal. All right, let's try another one. The weights in pounds of a basket of potatoes from two different vendors are recorded below. Assume that the weights from each vendor is distributed nearly normally. So vendor 1 has weights 15, 17, 16, 16, 17, and 18 pounds. Vendor 2 has weights 14, 15, 16, and 13 pounds. Test the hypothesis the mean weight from the two vendors is different using alpha is 5%. Construct a 95% confidence interval for the difference in the mean weights from the two vendors and provide their summary statistics. Press pause now. All right, hopefully you worked this out on your back. You realize that this is not paired data. They're not even the same sample size, so that's certainly not. They're independent samples. So this is a two-sample situation. If each vendor weights are distributed normally, or at least close to it, then we're doing the hypothesis testing here on two independent samples. The population standard deviation is not given to us, so this is a two-sample t-test and a two-sample t-interval. So we just run those programs on the calculator. First, we need to put our two datas in. We're going to do vendor 1 in list 1, vendor 2 in list 2, and the test and the interval will be done on vendor 1 minus vendor 2. It's not done pairwise, it just finds the sample mean here and the sample mean here and does the difference. So anyway, we run a two-sample t-test. We say our data is list 1 is the first list, the second list is L2, and frequencies are 1, and we just want to do a not equal here, right? Test hypothesis of two vendors is different, so that's not equal. Choose no for pooled. I think we always choose no for pooled. And it will return, yeah, here it is, this one right here. The alternative hypothesis is that mu1 is not equal to mu2. Of course, the null hypothesis is that they are the same mean. The t-test statistic is 2.58. The p-value is 0.045. And we see the degrees of freedom and the x-bar values and so forth. And then I think actually the standard deviations and the sample sizes for each. Well, the main thing we want to pull out of that is the p-value is 0.044. Alpha was 0.05. P is less than alpha. We do have enough evidence to reject the null hypothesis. So especially when we do that, we need to get a confidence interval go with it. So we use a two-sample t interval. That data. And then that's a two-sample t interval program. Run it. It's the same information that we had for the t-test. In fact, it's already probably all going to be in there for you if you just did this one. You just have to put in the confidence level, choose non-pooled, and tell it to go. And it computes our interval for us, which is somewhere between 0.0689 and 3.931. And it returns the summary statistics about degrees of freedom and x bar 1 and 2 and standard deviation 1 and 2 and so forth. So summarizing that in this table here, we see that vendor 1 had a mean of 60.5 pounds, standard deviation of 1.0488, and a sample size of 6. Vendor 2 had a mean of 14.5 pounds, a standard deviation of 1.2901, and a sample size of 4. The difference in sample means is 2 pounds with a 95% confidence interval for the difference in population means, vendor 1 minus vendor 2, to be 0.069 pounds up to 3.93 pounds. A two-tailed test of hypothesis referred a p-value of 0.045, so at the alpha equals 5% level, there is sufficient evidence to conclude that the mean weights from the two vendors is different. A manufacturer claims that 75% of the calculator owners prefer their brand of calculator. A sample of 15 calculator owners were surveyed and it's determined that 53% of them prefer the brand of calculator in question. Is there enough evidence that the alpha equals 0.05 level to determine that the manufacturer's claim is inflated? Press pause now. Okay. Note that we are testing proportions and the population size is large and unknown. So we should use a binomial distribution to compute a p-value. Notice this is a left-tailed test. Notice that in the sample we also have p hat is 0.53 times the sample size of 15. That's 7.95. So it's really 8 people that are preferring the brand in question. 8 out of 15 rounds off to 53%. So the p-value is the probability of getting a sample of size 15 with 7 or fewer successes from a binomial distribution, with a p-value, not a p-value, but a p, which is a proportion of successes or probability of the success, to be 0.75, and n is a sample size of 15. The easiest way to do this is to use my program over here in red. So it's a purport 1 program. That's a hypothesis test. 1 sample, proportions. Sample size is 15. Number of successes in the sample is 8. It's a left-tail test. Population size is unknown. It says the proportion of successes in the population is 0.75. The p-value given by a normal approximation, which would be what a 1 proportion z test would give you a p-value of 0.026. The binomial approximation, which is much closer and is the best value we could get here, is 0.056. At the 0.05 level, there's not enough evidence to determine the manufacturer's claim is false. Notice you would have gotten a different conclusion had you used the normal approximation here. Okay, and notice here is the 1 proportion z test on the calculator. Again, you're turning the same p-value as given right there. We see that that's not appropriate. The actual p-value is determined from a binomial CDF, which is done here, which is what this program is using. So in any event, we do not have enough evidence to reject the manufacturer's claim and say that it's false. All right, let's try another problem. A national mathematics tutoring company claims that 90% of its customers show at least one letter grade in improvement in mathematics. To test this claim, a survey of 500 of its customers taken and found that 85% of them showed at least one letter grade improvement. At the alpha equals 0.1 level, is this sufficient evidence to conclude that they have exaggerated their claim? Construct a 90% confidence interval for the population proportion of customers who show at least one letter grade improvement. If acceptable, use a normal approximation. Let's pause now. Note that with a large population size, the sample size of n is 500 is greater than 30, np is greater than 30, nq is greater than 30. These sizes are sufficient to make a normal approximation of the binomial, which is really an approximation of a hypergeometric distribution, acceptable. We can use the 1 proportion z test, 1 proportion z interval in the calculator, and they'll be okay. We could, of course, also use our report 1 program as well for the probability, and it'll do the 1 proportion z test anyway. Using a left-tailed test of proportions using a normal approximation, we obtain an approximated p-value of 0.00097. 4 zeros there. So there is strong evidence. It's very close to 0. So there's very strong evidence that the company's claim is exaggerated. A 90% confidence interval for the true proportion of its customers showing at least one letter grade improvement is, well, it's 82% to 88%. Now, how do we find these? We used our program. We just used a 1 proportion z test. The p-naught is 0.9, because they claimed it was 90%. The x value is the number of successes. That is 85% of 500, 0.85 times 500. That's NP here. Oh, not NP. It is P hat times the n. So it's 0.85 times 500. Okay. And that's 425. N is 500. We're doing a less than, so it's a left-tailed test, and we calculate that. And here we get a p-value of 0.40 and a 9 and a 7, let's say. P hat is 0.85, which we knew, of course, and N is 500. We do a 1 proportion z interval. Then that would be a x is 425 again. N is 500. Confidence level is 90% confidence level. Yes, so it's 0.9. Calculate that, and this is so anyway, this interval is from 0.823 to whatever, about 82% to 88%. So there, we're 90% confident that the true proportion is somewhere in there. and which is lower, definitely lower than the 90% that they claim. We have a very low p-value, so we're very confident that they've inflated their claim a little bit. The actual p-value, really you would compute it from a binomial CDF, which is what I've done here. It's 0.3 zeros and a 2.8, and this one was 0.4 zeros and a 9. So it is off a little bit, but they're both so extremely small that you know, there's no difference in really using those. So the one proportion z-test was legitimate to use. In a recent survey of approval ratings of a politician, it was found that 35% of 120 women and 53% of 100 men approved the politician's performance. At the alpha equals 0.1 level, is this sufficient evidence to conclude that women and men have different approval ratings? Construct a 90% confidence interval for the difference in population proportion of men and women who approve the politician's performance. If acceptable, use a normal approximation. Press pause now. We see that the population size is large. Both NP and NQ are greater than 30 for both samples. So a normal approximation is appropriate. So we can use the 2-prop z-test and the 2-prop z-interval in the calculator. So here we run the 2-prop z-test. We put in the number of successes. And the first one, let's see, 35% of 120. So it's 0.35 times 120. Is 42. Okay, that's right here, N1P1. And N2 P2 is 53. That's what? That's 53. Well, it just says 53 of 100, so that's already told us. That one we didn't have to multiply. So anyway, that gets these four numbers. We're just doing for difference, so we do not equal to. Calculate that. There's our test statistic and so forth, all the information about the proportions. And then the main thing is this P right here that doesn't have anything on it, just a straight OP. That's our p-value, 0.007. So that's pretty strong evidence that there is a difference. And certainly compared to the alpha of 0.1, this is quite a bit smaller than that. So there's strong evidence to say that there's a difference in men and women. Well, how much difference? Let's do a 2-proportion z-interval. So with the same inputs here, confidence level of 90%, and then calculate, and we get this. The negative indicates that the first one is smaller. So women minus men is, so women are less likely to support the candidate by about about 29% to about 7% less than, proportion would be less than the men. So the average is the true proportion, where 90% sure is somewhere in there. The difference in the proportions is in there. A manufacturer claims that the standard deviation in mass of one of its products is 25 grams. A sample of size 25 is taken as a sample standard deviation of 27 grams. We know that individual masses are distributed normally. Is there enough evidence that the alpha equals 0.5 level? 0.5 level. I think we probably want 0.05 there. Alpha, of course, needs to be something small. We want to conclude, is there enough to conclude that the true proportion, true population standard deviation is larger than the claimed value? Okay, now this is about standard deviation, not means. So if there's anything here about masses or whatever, about means, that's irrelevant. Let's see, we just need the standard deviations. Yeah, there's the sample standard deviation. No, that's the population standard deviation is by the null hypothesis. There's a sample size, there's a sample standard deviation. Okay, so we need the individuals to be distributed normally. We're told that that's true. Then we can use our techniques. We can use the hypothesis test and confidence intervals for the standard deviation. This is our SD test program. So we just run that. It's going to ask us for the N, which is the, let's see, I think it'll go across this way. The interval for one's populations, we ask it for the sample size. N is 25. Sample standard deviation is 27. Okay, which it just returns that. Then we have a choice of inference only or inference and hypothesis test. We'll do both, so we choose 2. Then it says the null hypothesis is that sigma sub x's is what? It's 25. The test statistic chi-square, it returns here. Okay. Then we have to decide if it's left or right-tailed. This one's right-tailed, or two-tailed. This one's right. And it returns a p-value for us right here, which is big, a lot bigger than 0.05, so we do not reject the null hypothesis. And to do the confidence interval, then it's going to ask us for a confidence level, which we put in 0.95, and it gives us this. So we're 95% sure that the true standard deviation is somewhere between about 21 and 38, and they claimed it was 25. So we certainly have no evidence to suggest that they're not telling the truth. So with a p-value of 0.26, much bigger than 0.05. This is the page that would do it if you did not have the program. We would find the test statistic this way. Chi-square is n-1 times s squared over sigma squared. Plug in the numbers as you see right here, and you get the 27.9936. And I just stored that as x, which you can see right here on the calculator. I did 1 minus the chi-square CDF from 0 up to that x value with 24 degrees of freedom. 24, of course, being n-1. That's our p-value right there. To do the inverse norm, if you don't have any of my programs, you're going to have to do it this way. For these two values right here, for the lower and upper chi-square values, we take that 5%. Again, that should be 5%. And take that, split it in half. That leaves 0.025 to the left of the lower chi-square, 0.975 to the left of the upper chi-square. Graph those two horizontal lines in the chi-square CDF, calculate those intersections, and that gives and store them as L and U after I do them. So store this, get this one out, store it as L, get this one intersection, store X as U. And so now we have those lower and upper. Plug them in this formula here to get our limits for our confidence interval. So that would be the no calculator program version. The standard deviations of two sample masses of a product from the night and day shift were 25 grams and 29 grams respectively, with sample sizes of 27 and 38. Assume that the individual masses of both are normally distributed. Test the hypothesis that the shift has different variability in masses of the products that they produce. Use alpha as the 0.1 level. Okay, see if you can do that. Press pause now. Okay, well, this is a two-sample situation where we're testing standard deviations or variances, and that's an F-test, two-sample F-test, which the calculator has that built in. So just use the calculator wizard, enter in the statistics here, standard deviation of the first group, the sample size, standard deviation of the second group, sample size, not equal to, because it just said different variability, so that's a two-tailed test. Calculate, there's the F statistic and so forth, but the main thing is right there is the p-value 0.43, so there's not enough evidence to suggest that the standard deviations are different for the day and the night shift. And that concludes this set of videos over these review problems.